Hi calculus students. We're going to carry on from the notes that we started in class. In class we learned about the derivative function, which is a function very similar to that of our tangent slope. This function looks a lot like our tangent slope. The difference is that the tangent slope gets you a particular value for the slope at a given point. So for instance, we could find the slope of the tangent line at x equals 2, and it would give us a value for the slope to create a tangent line. The derivative function does essentially the same thing, but instead of finding the slope at a particular value, we do it for a generic value of x, and we end up with a function. So we did an example in class together, and I want you to try this one on your own. So pause the video, try it on your own. And after trying it on your own, you should have ended up with f prime of x. So you did a bunch of work. F prime of x equals 2x minus 2. If you did not get this, please find your error and correct your work until you get f prime equals 2x minus 2. So once you have this derivative function, it helps you to find the slope or the instantaneous rate of change at any value of x. So down here it says, how could you find the instantaneous rate of change of f of x at x equals 3? So we will use our f prime and we will evaluate it at 3. So f prime of 3 equals 2 times 3 minus 2, which is equal to 4. Okay. So this tells us that our function has a slope of 4 at 3. So I'm going to write this as a sentence. So at f of 3, the slope of the tangent is 4. Okay. And just because I always like to look at things graphically, we can draw a little picture of this. So this parabola has a vertex at 1, 1. It intersects at 0 and 2, and then it has a point at 3, 3. Looks like this. There's the parabola. And then I will do my derivative function in red. The derivative function is the equation of a line that intersects at 2. So I'm going to draw this. And it goes all the way up to 4. So it intersects at 2 and has a slope of 2. So up 2 over 2, up 2 over 2. Okay. And so we see at this point 3, the output of my derivative, my f prime, is equal to 4. And what this is representing is that at this value of 3 on my original graph, the tangent line, if I were to draw a tangent line in here, so I could draw a tangent, the slope of that tangent line would have a slope of 4. So down here, this is the alternative definition of the derivative. It means the same thing, so it's not like we're saying that the derivative means something else. Essentially, there's just another equation that you could use if you want to. This equation honestly makes a lot more sense to me, and the reason why is because it looks a lot like the slope of the secant. So down here it says the slope of the secant line is the change in y. I know this printed poorly. It's change in y over change in x, which is f of x minus f of a over x minus a. So it's just our change in y over change in x here. But we're looking at it when the limit as x approaches a. So this is supposed to say the limit as x approaches a. So it's saying as these two values, a and x, as a and x get closer to each other, so as x approaches a, basically the secant line is going to get really, really close to each other, but we can still use that secant equation, like the f of b minus f of a over b minus a. We can still use that equation there. So this equation is the same thing as our other one, the limit as h approaches 0 of f of a plus h minus f of a over h. It's the same thing, it's just a different form of it, but it functions in the same way. So if you prefer this equation, you can use that. I'll just show you an example of how you would apply it. Oops. So right here, our alternative definition. Okay. So I'm just going to write it up here. Our alternative definition looks like this. It is so it's still f prime of a, and it is the limit as x approaches a of f of x minus f of a over x minus a. Okay, so that is our alternative definition, and we can apply it here to find the derivative, which we can call differentiate. So differentiate is the verb to find the derivative. So f prime of a equals the limit as x approaches a. F of x will be square root of x squared minus 1 minus f of a is a squared, the square root of a squared minus 1 all over x minus a. So just like in the other case, if I try to plug in a for x, if I try to substitute in, I get a minus a in the denominator, which is 0, which is not allowed. So just like before, when we wanted to cancel out h, now we just want to cancel out this x minus a. Okay? And so to do that, we're going to simplify the numerator until we can cancel out x minus a. This requires multiplying by the conjugate. So we have these rational functions, we need to multiply by the conjugate. So the conjugate here will be square root of x squared minus 1 plus square root of a squared minus 1. We do that on the top and the bottom. And when I do this, the numerator simplifies a lot. So the square roots drop away and I get a squared minus 1 minus, I need to make sure to use parentheses because of the minus sign. This term times this term becomes a squared minus 1. That. The denominator I will leave in factored form because I want to be able to cancel stuff out. Like that. Okay. So if I look here, I see that I have like minus 1 and then minus negative 1. Negative 1 minus negative 1 ends up canceling out. So those go away. And in the numerator, I have x squared minus a squared all over what's in the denominator. And those of you who know your factoring know that this is a perfect square that we can factor. So we can factor the numerator to be x minus a times x plus a. The denominator stays the same, this factored form. And now it's finally clear, woohoo, I can cancel out right there. And now that I've canceled that out, I can apply my limit as x goes to a. So I'm going to plug in a for my x's, and I get a plus a up there. I get the square root of a squared minus 1 times the square root of a squared. Oh, why did I turn this into times? This should have been plus. My bad. So since I multiplied times x squared, the square root of x squared minus 1 plus the square root of a squared minus 1, I should have had pluses here. I messed up. So this is plus, this should be plus. Okay, so this is a squared minus 1 plus the square root of a squared minus 1. So this becomes 2a over 2 times the square root of a squared minus 1. The 2's cancel out to become a over the square root of a squared minus 1. Oops. So that is my f prime of a. My general equation for the derivative. Okay. So if you like the alternate definition, you can use that. It works the same way as the other definition. Your choice. You should be able to recognize both though. So both limits you should recognize. Here's just a little follow-up question. So now find the equation of the tangent line at x equals 2. So tangent line, we should always just remember this is just the equation of a line that uses the slope, the tangent slope, at whatever x value we have. So if I need to find the point, my x1, y1, we will use our x value. So we will use our original equation. So my f to find the point. So since x is 2, I will plug 2 into f. And I get 2 squared minus 1, which is the square root of 3. So that is my y value. So my point is going to be 3 square root of 3. And then to find the slope, I will use f prime of 2. So for my point, I get x1, y1 by using the original function. The slope, I use f prime. So f prime of 2 will equal 2 over the square root of 2 squared minus 1, which is 2 over square root of 3. We could rationalize this. I'll just leave it like that for now to make this more simple. So I'll plug this into my equation for the line to get y minus square root of 3 equals 2 over the square root of 3 times x minus 2. So there's that. And just do a few more notes. So we could look at this derivative notation. So far we've been using this prime notation, like that. Prime notation is definitely the most simple, but the least informational. So can you take 30 seconds and read this, and then I will summarize it for you. So go ahead and read this. Okay, I'll come back in. So basically there's a lot of different notation because both Newton and Leibniz, if you remember, thought they invented calculus at the same time. So they came up with different notations to use. So Newton came up with the very simple prime notation, and this is nice because it's just very short. It's easy to write, but it doesn't really give you as much information as Leibniz's notation. So Leibniz notation may seem very confusing at first, but it actually gives you some really great information. So for instance, the d's that are always here, they stand for derivative. Okay, so the d just stands for derivative. and then y, x, or f are just representing the variables that we're using. So very commonly we use this dy dx, the derivative of y with respect to x. So y is the function we're taking the derivative of, and x is the variable that is used in the function. Really similar is this df dx. So this is just if we have a function name, like if the function is called f of x or g of x or h of x, we could say df dx. So the derivative of f with respect to x, the variable. And then this is just like a third way this could be written. This is just really making it clear that differentiation is an operation that we're performing on the function. All of these mean the same thing. They all mean take the derivative. Okay. So we're just going to apply this. I honestly think I did these in the wrong order. So we're going to apply it here. So example 4, we should be on example 4. And we're going to just use our notation correctly. Okay. So understanding our notation. So all of these want us to use the same f of x. They're all using f of x equals 3x squared. And so I will just cheat and let you know that what this means is that f prime of x equals 6x. Okay? I'm not going to make us do all the work to find that. I will just tell you that. So here's the basic prime notation. These examples are using slightly more advanced notation. So in part A, we have d dx of f of x. This means take the derivative of f of x in terms of x. And then it tells you the function. So this is the same thing as this. So we're using this function. So I'll say d dx of 3x squared equals 6x. Same thing. Yeah, same thing down here. This is the derivative. Here they just directly wrote it in instead of writing it all out like that. So the derivative of 3x squared in terms of x with respect to x is 6x. Very similar to part A, except here they have this little line and then an x equals 2. So this is saying find the derivative of x and plug in x equals 2. Okay, so find the derivative of x and plug in x equals 2. So this is going to be equal to d dx of 3x squared when x equals 2 equals 6 times 2, which is 12. So we're solving the derivative at x equals 2, plugging that in. And D says the same thing as C, except using prime notation. F prime of 2 means find the derivative when x equals 2, so that is also 6 times 2, which is 12. So all of these are just different ways of saying the same thing, and you have to recognize all of them. You must recognize all of them. So the last problem that I'll have you do is this u-try. So I want you to try this problem on your own. Please pause me, figure out what this notation means, and then do it. Go ahead. Okay, here's my work. So I just found the derivative of 1 over x by using my limit. I used the normal limit definition. So I took the limit as h approaches 0 of 1 over x plus h minus 1 over x over h. And I did a bunch of algebra to cancel out the h's. I determined that my derivative function was negative 1 over x squared. So you should have got negative 1 over x squared. If you did not, go back and find your mistake. And then, because of this notation here, this means solve it and plug in x equals 1. So I plugged in x equals 1. to get negative 1 over 1 squared, which is negative 1. So what this is saying is that the slope of the tangent when x equals 1 is negative 1. So this represents the slope of the tangent when x equals 1. I'm going to stop here for now. We will do more when you come back next week. Have a good weekend.